All right, hi everyone. This is our first video on introducing us how to use R. So we have labs each section where we cover, statistical analysis in the software SPSS. And in those labs, I tend to go pretty slow. We look at the data, we interpret the data, and I try to get a lot of feedback from the class. So the purpose of this video series is different. It kind of is meant to complement that. So I'm not going to interpret and go into all the details like I would there. Here, I'm just showing you how to do basically replicating what we do in SPSS over here in R. And so with that said, let's go ahead and get started. So, I just opened R, and the only thing I'm not going to cover is how to install R. There's a lot of walkthrough videos on YouTube and other resources online. I'll say one thing: you need to install two things to get going. One, you install R, and R is a programming language, and it does have its own interface and all that. But secondly, you're going to want to install RStudio, which is what I'm showing here. And RStudio is a program that's designed to complement R. And it basically is just all this software, its interface, and it makes R much more powerful because it's just it's a much more user-friendly way of using R. So definitely get both R and RStudio. RStudio should be installed second, and then you're ready to get going. So with that said, let's go ahead and get started here. So what we're looking at here is when you first open up RStudio, you're going to notice that there are, what we call panes, and there's really 4 panes. So, I was hiding a pane up there, and that's how mine just opened up. And you just hit these minimize and maximize buttons. I think it's pretty intuitive. And so we'll start in the bottom left, which is what we call the console. Don't need to worry about the terminal tab. So in the console, this is where you're just going to execute basic code. So R is a programming language, and as you get more comfortable with it, you'll be able to type in more complex things. But at the very beginning, I think it's good if you're learning R to think of it as a calculator. And it's much more calculator friendly, and how you can type in, store results, see your past queries, as compared to more traditional calculator-based software on a computer. So when you're learning R, and if you ever need a calculator, I definitely think a good place to start getting comfortable is coming here and using it as just that at its most kind of like elementary use. Now, the second pane that we're going to introduce is over here in the bottom right. And each little pane, they're going to have different tabs. So this is files. It lets you see all the files on your computer. You can interact with and change the files and stuff like that. Use a little checkbox. It's pretty clear. If you need to navigate to a certain folder on your computer, maybe you need to go find a data set. That little 3-dot thing right there will pull this up, and then you can navigate to wherever you need to on your computer. Plots, that's going to be empty for us at this moment, but we'll see some plots filter in here in a little bit once we execute the commands. Packages, I'll say more on this later, but I'll note that R comes with what we call packages, and each package is basically a set of commands that you can execute in R. So it's a very simple way to think about what a package is. We can also call them libraries because they load sets of commands or functions for you to use. And then we've got the help menu. We'll be looking at that in today's video. Don't worry about the viewers. So I usually will come over here to file, the files tab when I first start in R. Up in the top right, you'll see we got, again, tabs. So the environment, we'll come back to this in a little bit again once we actually can see it populate. Right now, it's just empty. And I'll explain what it is then. History does what you probably think it does. It just saves all your commands. And if you have multiple R projects and stuff, you have different history files. So it'll save the history unique to whatever project you're working on. Here, I'm just kind of in my general R. So it's kind of like whatever I've been doing recently. Connections, don't worry about that. That's for connecting to external databases. When you start using R and any statistical software, usually you're going to be using data files. So like a CSV file, stands for comma separated values. I've got a lot of files online that are, SPSS files. All of that you can import into R. And so, you're not going to really use the connections. You'll import your data, and then once it's in your software, you can start manipulating and interacting with that data. Finally, we have the source up here. So you saw I just hit the little thing to expand it there. And right now it just opened to a blank code file. We call these code file R scripts. Now, when you first start learning, you can mess around in the console for a little bit, but it's not long before you desire to start saving your code. So you can kind of come back to it and keep, maybe you left off at a certain point and you want to keep, growing it, or you want to save it for later study. But, you can type stuff here and it'll save your code, and then you can execute the code. And when you execute, the output will always be down in the console. It shows you what you execute or tell R to compute in the blue, and then the black is going to be the output. And so, again, you're really going to want to save these R script files pretty quickly, maybe not the very first time, but like second, third, fourth use, you want to start kind of creating your own code so you can come back. And it's hard to remember when you start studying a new programming language exactly how everything works. So do yourself a favor and save your commands that are common here. And right now it's called untitled, and when I close this, it's going to ask me to save. I'll just hit no because I don't want to. And then up here, the only thing I really use in these menus is I use the tools, and I'll go down to global options. Notice you also got keyboard and shortcuts, and I'll be talking about some shortcuts today, but when you do syntax-based language, really good to know some of the essential shortcuts you use a lot. And so there's a lot of options here. I don't have any like major things I would tell you about good default options at the beginning. As you use R more, you might develop a preference. You can, for example, change the color scheme and all that. Some people like to do that. I usually just leave it like this, and it's, default settings. And then I don't really use anything else up here. Sometimes I've come to view, and you can see it just allows you to kind of just view different things that's going on in your data session. And sometimes I come to file, does the usual things. So with that said, let's go ahead and load our first R script. So I suggest you create a folder on your computer that you're going to save all your R documents and files and outputs in. So here I have one called R Labs, and make sure you create these three folders because you're going to need them to run the code, and they've got to be the same exact names: code, data, and output. I'm sure you can guess what goes in each. So let's start with the code file. I'm going to open the folder, and right here we have our first R script we're going to look at together. So I hit enter, and it opened. Okay, so the very first thing we want to say, R is syntax based, which means you're going to be developing code and saving code. And one of the most important things is organizing your code well, because it can be a nightmare if you've shared code. It can be, if it's not well organized, it's kind of confusing. And so one of the most useful things to organize your code and keep your thoughts clear are comments. So we talked about comments in the lab. Comments basically ignore a line of code. So you can see I can type as messages here, and R will just ignore it. It won't make the program crash or lead to an error, because this is just a basic sentence, not R syntax. And the comment is indicated right here with the hashtag. So like, for example, no comment on line 6. If you hit Control Enter, or maybe it's like the Apple return on a Mac, you can execute that one line of code, and you see it executes. You see the 11 there. But let's say I put a hashtag in front of it. Now, if I execute that line, R just like ignored it, and it went to the next line that it could execute, which was the very next line, number 7 there. So that's a note on commenting out code. The other thing I'll say on organization, there's this little like menu looking thing over here. And if you hit that, you can kind of jump around to different sections in the code. So I'm not sure what all the shortcuts are in Mac, so you're going to have to kind of look these up. But I know in Windows, if I hit, I think it's Control-Shift-R, yeah, section label. And there you go. It puts it kind of in a nicely formatted new little section for me, and it added to the table of contents over here. So that's really useful for as your code files get longer, just organizing them in a nice manner like that makes it easier to navigate. So let's go ahead and get started. So looking at our first commands that we're going to execute together, you'll notice again, they're just little math things. Again, thinking of R as a calculator and learning it that way is really useful. So there's here a logarithm function. So the creator of R said that everything in R is either an object or a function. I'm going to come back to an object in a little bit. But a function, if you remember back to your high school days, it takes an input and gives you an output. That's all it is. We'll be talking about linear regression, which is it's a linear function this semester a lot. And so you can tell it's a function in R if it has parentheses. So this is the log function, and you see how it has a set of parentheses that close. And then this 6 times 5 is the input to that function. So, you can go ahead and execute all this, and you'll see it just takes the log of 6, and then here it adds it to the log of 5. That turns out to be the same thing as line 7. They're mathematically equivalent. Doesn't really concern us that level of detail, but you get the same thing either way. And I'll also note that I have the exp function. This is the exponentiation function. You can put a function inside another function. So here I put the log 5. The log is a function with an input of 5. That's going to generate an output. So look, I have it just that part of the code highlighted, right? If I hit Control Enter, I can execute just what's on the inside there. So what's going to happen here is that is first going to evaluate on the inside, create a 1.6, and then that 1.6 will get fed to the exp function. And so a little note on our first functions there. Now, R also supports what we can call Boolean logic. And so Boolean logic, it's true or false. And this is true in basically all programming languages. We map true to the number 1, and we map false to the number 0. And at some point, if not today, but some point in this video series, you'll see why that's actually pretty useful. And so what that means is I have the Boolean true and false here. And if I actually take the sum function with true and false as the inputs, you can see we're going to treat false as a 0 while we treat the true as a 1. So that's very useful to know. And there'll be some times where that summing of the true and false becomes really useful, because you can imagine I have like a column of data. I want to know how many people are taller than 6 feet. Well, I can kind of create a logical expression and then just sum it, looking for the data points that are bigger than 6 feet. Okay, and now we're going to talk about assignment operator. So the assignment operator is this thing. It's a less than sign followed by a minus sign. This lets you store values. Assignment operator. You're assigning values to variables. So here, we're storing the value 65 in X. And when we do that, notice now the global environment is no longer empty. So you can think of the global environment as all of the data objects that you currently have access to call and manipulate and interact with. Now, I just came back to that word data objects. Remember, I said everything in R is either a function or it's a data object. And not like everything, but that's what the creator of R said to help us learn it. And it's a very useful way of thinking about R, because what we've just done, we stored the value 65 in a data object, which we labeled X. So we called it X, we could have called it anything. We could have called it elephant or zebra or, lion. It honestly doesn't matter. You can name it whatever. But of course, we prefer short things that are easy to recall. And when you have a large data set, you're going to want to give them good names, right? Like, and we'll see some examples of, good naming conventions throughout this semester. But the nice thing about storing it in a data object is it allows you to now call that object. So first of all, when I executed X, this line 16, look what it did. It just said 65 goes into X, but it didn't return a value. And when you store something, it doesn't return it unless you ask it to. How can we ask it to? Well, we can just go ahead and execute X and it will print what's in X. Now, look, if I come down here and type Y, it's a capital Y, not that it matters. Error, Y is not in our environment, so R doesn't really know what to do. So it's just going to throw an error message. Now, we can also do, we can take our X object, which has just one value of 65 in it now, and we can subtract 10 in it. So you can save outputs and results and kind of keep manipulating them and moving through code in a systematic manner. So when it did X minus 10, it evaluates to 55. Notice that X is still 65 because we did not assign a new value to X. And you could actually test that out. You could actually come in and you can see if I were to do that, X just went to 55 after I assigned it. Now, you might notice I created this assignment operator pretty quickly. So the shortcut on a Windows is Alt dash or Alt minus. You're going to have to look it up on a Mac, and I definitely suggest you learn it because you're going to be hitting it so often. Now, line 19, you can probably guess what it's doing, right? On the right-hand side, we're going to take our 65, subtract 10. We're going to store it in a new object called Y. So we execute it. The console doesn't output it, but the value is there in our environment, and we can call it now that Y is in the environment. Now, you can also use an equal sign for assignment operation. I do not suggest you do that. It's very rare that you'll see programmers do that. There actually is some obscure reason why this assignment operator is better. I can't remember what it is, but you just will never see people using the equal sign. But they work mostly the same. But even still, definitely prefer the assignment in line 22 as compared to line 21. Okay, so R is case sensitive. Now, not all syntax languages are, but this is true in R. So this is a capital X. So capital X is not in the environment. So R is going to throw an error. So you've got to remember that it's case sensitive. And if I made it like the word pilot with a capital P, I've got to type the capital P. And so you see it's got a capital P in the environment. R is very sensitive like that. Now we can also create lists of values. So what we're going to look at next is we're going to create a list of 1 through 10. So you execute it and you can see the result. We go from 1 to 10 incrementing by 1. So that little colon, it basically tells us to create a sequence where you have the starting number on the left and the starting number on the right, or sorry, ending number on the right, and it jumps by 1 each time. Now there are other ways to do sequences. You can, go up by 2 or 2.2 or some kind of crazy pattern. And as you learn R and you need those kinds of things, they're really easy to Google and figure out. But this one you'll use a lot. This colon, it's a pretty common operation you're going to use in R. Now, earlier we assigned a single value to the data object X. Turns out we can store a whole bunch of values in one object called X. And when we do that, we actually call X a vector. And so what is a vector? You can think of a vector as basically just like a column of data. And here, there's 10 numbers. So the vector, it tells me it's an integer vector. And it goes from, as you can see, 1 through 10, and it has 10 values in it. And notice again, I executed, it didn't print. You can see it in the environment, but you can call it at any time, and you can get it to print out whatever the output is. Now, going back to this analogy of everything's a function or a data object, usually your data objects are going to be the inputs to your function. So this is the length function. I can call it on a vector, and it will tell me the number of values or elements saved in that vector. And you can see there it returned 10 because there are exactly 10 numbers in our little X data object. So the next fundamental skill we want to build up is subsetting. So subsetting, think about what a subset is, right? If you have a bigger set, a subset is just a more narrow set of values, right? And so the subsetting operation is the big brackets, the square brackets. So if I do X square brackets and then put a 1 in there, it's going to take out the very first value. And now a little thing note on language, we call these actually elements more commonly than values. So that would be the first element, that would be the second element, that would be the 10th element. So if I call the second element, it's going to print out 2. Now the second element happens to be the number 2. It could have been a 6 though, or whatever. It just depends on what is in that data object X. You can also call for range of elements. So again, I'm going to execute the 5, 7, and you can see it's telling me to pull out 5, 6, and 7. So when I pass that inside the square brackets, it's going to take out the 5th, 6th, and 7th elements, which happen to be the numbers 5, 6, and 7. Now you can have an integer value or integer vector. You can also have a character vector. So this line, we read this little c, it's saying it's a function. It's always a function if it has parentheses, which means you need to put stuff inside the parentheses usually. And this is the concatenation function. And concatenation, to concatenate simply means to combine. So here I'm just taking a few different strings, example of a character vector. And when I execute that, notice it saves it in my environment. Now it's a character vector. And it's got, again, it has 5 different elements. And I can look at the length of a character vector, just like I did earlier on an integer vector. And now there's 5 unique elements, so it returns a 5. No, I can also chain this together. I could do like length -1 if I wanted to. So, R, you really want to learn the building blocks like this. And then it's kind of enjoyable when you start being able to kind of build it up and combine stuff like that. And then now I'm going to just execute the X object. And there you go. You can see that it just simply printed the 5 character strings that were saved in that vector. I can also pull out the second element, which of course would be of. It's in the second position. I could pull out the second and third. Notice how there are 2 different values. You can even, again, you can put the length around that. And because there's 2 values, it'll tell you there's a 2. So you can control Z and R. I don't think actually control Y, which is like undo or redo. It's called the redo. It doesn't, I don't think that works. Yeah. Now, okay, we can have integer vectors. We can have character vectors. There's a function called class, which when you run it, it tells you what is the underlying data object. Okay, so now we're going to move on to vectorized operations. So line 46, we're going to store the values 1 through 10 in X. So we turned X back into an integer vector. Now for Y, we're going to take, so this is what vectorized operation means. you're multiplying each element in the vector by 3. So what do you think y is going to look like? So I execute it, and hopefully you were able to guess that it was just, each element 10 times 3, 9 times 3, and the 3 gets applied everywhere. So very compact way to write it, and it produces, a lot of output, right? So it's pretty concise, this programming language. And so, you store it again. When you have hundreds of values, you can't really use this to look at them. So using this to print out your data is pretty useful. And there's another way to print out your data, which when you have thousands of rows is just, even this isn't really going to be, it can get kind of crazy in the console, the data viewer. So I'll show you how to do that later once we get to a data set of sufficient size. And as usual, you can subset it, ask for different values, and look, y is a numeric vector. So R makes it pretty easy to visualize your data as well. So here again, I'm creating an integer vector. Now y, this time what we're going to do, we're going to multiply each x by 2 and add 10. It's actually a linear function. We'll be talking about linear functions in class in the very near future, but there's two parts of a linear function. There's an intercept and a slope. We'll be getting very comfortable with both this semester. And so I've stored x, I've stored y, now I can plot it. And you'll notice my plot pane has automatically popped up now that it's relevant. And you can click in zoom, and you can get a nice view of it. You can copy, you can save the image, and all of that. Now, here I'm going to show you an exponential function. So I'm not changing x. I'm just going to change y. And now I'm going to plot that. So what you're going to notice, first, look at the axis. It goes from 0 to like this really huge number. What is this, 200,000? And note how it looks like there's no movement from like 0 to 6, a little bit of movement up to 7, but really 0 to 7, not moving much. And then it just takes off. And so, this is kind of like one problem when there's outliers. It can make plots kind of unreliable or kind of misleading, more rather. And so what we can do is we can leave off the two biggest outliers. So how would we do that? Well, here, the way I've done it is plot takes two arguments. Plot is a function, and there's actually other kind of plots you can create with this. I created a scatter plot. And so scatter plots need an x-axis and a y-axis, and we put the x first. And so what I've done to hide the outliers is I've come into x, but look, I've applied a subsetting here. That's what the brackets mean. So the negative, so let's focus on that second, actually. So first, I did a little C function or concatenate function with 9 and 10. So if you execute that, it's just going to be the numbers 9 and 10. What the negative sign does inside of the subsetting thing, you can't use this in normal vectors, but when you're subsetting, you can. It tells me to select all the values except 9 and 10. And I did the same thing on y. I got rid of number 9 and 10, and I want to plot. Now you can see the movement in 6, 7, and 8. But again, it still doesn't look like there's much growth. But in an exponentiation function, the growth is actually the same proportion of growth from 1 to 2, 2 to 3, as it is from 7 to 8. But you got a bigger base here. But anyways, that kind of shows you can really combine this stuff inside of each line of commands and code that you execute, and are pretty intuitive way once you really learn R. At first, it can kind of be a lot, but once you get used to it, it becomes a feature how you can kind of embed code like this inside of functions that you really start to enjoy. It's quite powerful. Now, the plot has a lot of options. So let me show you guys the help menu. So if you type in question mark followed by a function, R will pop open the help menu. And here, we want to go to the default scatter plot function. So you can make this large, And then it will tell you about all the different, so we call these arguments. Each function, it has a set of arguments or inputs or parameters. All three of those mean the same thing. And, you know, like maybe I want to give it a title. Well, there's an argument for that, and it's called main. And how you know that is you come and you read this, or you look at other code online. Honestly, a lot of what we do is we learn from other code online. So you can get so many useful tips by just Googling plot function R, and really get some code, create some cool plots pretty quickly. You know, you can change the Y limits, the X limits. There's even different types of plots. What I will note that some of these have quotes, and they require, like when you type it in, if I were to type in, you know, type equals like A, or let me say it says P. I don't know what P is, but let me just put a P without a quote. It's going to give me an error because it's thinking P is some kind of object. But if I put it in quotes, it'll know exactly what I'm talking about. I guess P might stand for scatter plot. But you know, scatter plot is going to be the default when you have an X and Y, two arguments in here. And so you can define for functions, you can choose the parameters in two ways. You can do it by position, and that's what I've done here. The first argument is an X, the second is Y. You can also do it by name. So I could type in X equals X, and I happen to name the objects X and Y, so that's why it looks a little funny. But X, the first X is telling me I want the parameter or the argument X to equal, well, the data object X. And then you can see here, I've defined the main, again, you can see over here, it says null, but if you go read down here, I'm sure it'll have quotes somewhere. There's examples down below. And so I put the title in quotes, so exponential function. And then I also labeled the X and Y labels with titles now. So you'll see the X and Y labels there. I've got a title for the function, for the plot up there. And so, you know, looking online is going to be your best way to really learn how to do some cool plots. Now, this is kind of like an introduction, a quick crash course on, you know, the basic building blocks of R. If you're going to become really proficient in R, I would say there's this phase of 10 to 20 hours where you're learning so much so quickly, and every hour in it, you're really growing. And it can be kind of difficult to just jump in and start coding and doing statistics immediately. I definitely suggest you take the time and just go slow and use R. Look, R is free, and it's incredible. SPSS, once you graduate, if you only knew SPSS, it's kind of annoying because you got to buy it or buy licensing, and it's really expensive. So I definitely suggest you take the time to learn R, and you know, you'll always have it. And one of the best ways to learn R is there's this other thing called a package. So earlier I said I would come back to what packages are. And what a package is, we have two words for it commonly: package or library. They're synonymous. And what a package is it's created by some other user, like some random person in the world, and it does various things. It has various functions. Like maybe I want if I want to do, like, say, maybe I'm estimating an advanced model called a multi-level model. Well, someone has developed a package to do that. And if they're really good at programming it and making it user-friendly, it becomes really popular. And so, you know, there's several packages that you're going to really see a lot in R. One of the most common is ggplot2, which we'll come to in a second. But here, the swirl, it's really great way to start learning R. So notice I have a function install.packages, and I have to put it in quotes. It won't work if you don't have the quotes there. So I'm going to execute this. And what it's going to do is it's going to install this. So it basically is a set of usually functions or, you know, objects. It can be, you know, all kinds of things. But these other people created this for you to come and use it. Now, Swirl's a little different. They actually created this to teach you how to use R. So I installed it. It looks like it was successfully installed. And now when you have it installed, you need to first tell R that you want to use it. So you're going to call the library function. And I've always found this kind of annoying. You need it with quotes there, not with quotes there. I don't know why. But now I'm going to load it with R with the library function. And now I can start using Swirl. So once I type that in, look what it's telling me. Hi, I see that you have some variables saved in your workspace. To keep things running smoothly, I recommend that you clean up before using Swirl. And then it even tells you how to delete it. So look, this is a new function we're going to learn here, ls. It's actually pretty useful. It shows you all of the data objects you have saved in your environment. And it even gives you a command. This is a good one to save if you're going to create a code file for yourself for reference. And now it erased them. And so what Swirl actually does is it actually walks you through how to use R, and it's a really good teacher. I strongly suggest if you're a new user, definitely come to Swirl. So I'm going to type in my name. And then it's going to talk you through some things. I'm not going to go too much into it. Let's see. Also, I'm just going to continue, I think. Let's get started. Okay, and so you can see there are a lot of different kind of modules or things you can learn. Start with number 1 here. So I would hit number 1. And then I guess I had to hit number 1 again. And then it has these different options. And it talks about the basic building blocks and so forth and so forth. And it really builds up on itself. Once you make it through this first module in Swirl, you're kind of ready to kind of start doing some programming, some regression modeling. And I'm going to exit by hitting escape. And, you know, if you saw that there were other options, I think we can scroll up here. There is a regression models module. And exploratory data analysis, I could also see that being useful. But start with one. The other ones, if you have time and you're motivated, definitely are going to be useful as well. I've done a few Swirl modules myself back in the day. Okay. So with that said, that's kind of a crash course on the basic building blocks of R. Now we're going to look at an applied example. And so what we're going to do in this applied example below is we're going to use another package created by a user named Hadley Wickham. He's a really famous statistician down in, I think he's the University of Texas. And this ggplot is a data visualization package. So earlier we did base R, and it's pretty good, right? I mean, it does the job. But if you're trying to make like publication ready graphics, ggplot is considered the best, maybe of any software out there. Python has some ones that compete with R. When I've compared the two and done my research, people tend to have a slight preference for ggplot2, but really R and Python, they're kind of the gold standard for data visualization in syntax-based languages. There's other things like Tableau, which is kind of like SPSS. It's a graphical user interface where you point and click. But really, I don't think Tableau or any of besides Python, there's not much that can compare with R, I think. And you'll see how pretty the visualizations look in a little bit. So we're going to install this package. I will say one of the only frustrating things about being an R user is sometimes you try to install a package and it just won't, and it can be kind of annoying and frustrating. You're not alone. Other than that, R just works beautifully all the time for me. But there are sometimes I try to install a package and then it'll be like, oh, it failed to install because you need this other package, and you go get the other package, and yeah, it can be frustrating. But there, I was able to install, no problem. Now I load the library command to tell R I want to use the set of functions in the ggplot package. We'll be using them in a little bit. For us to use them, though, we need to get some data here. So how does R pull in data? So you probably noticed this import data. You can, of course, use that. Oh, look, there's even an SPSS feature. I do not suggest you use that. I suggest everything you do with code, because once you get it set up the one time in code, you can just always come back to a project and re-execute it. And in a second, you're good to go. You got your data imported. So to import data, we need to understand what's called a working directory. The word directory coming from the directory structure on your computer. Working is kind of where R is loading files from. So there's this function called get working directory or get WD, and you execute that. And it's going to tell you where R is kind of looking for documents and data files. But when you execute that, it's probably not going to be where you actually saved your data files for this course. So what we're going to do, I'm going to add a new command here. We're going to go get our data file. So I'm putting this on Canvas, but this data file is not the state's data file. We'll start on the state's data file next week. I'm going to come to the data folder here. And the file we're going to be using today is this one. It's called food supply quantity kg data. We can see over here, it's a CSV file. So what we have to do, I'm going to get the file path. I want to get our, actually, I'm going to create a project in a second. So don't worry about what I was just about to say. What I do need to do though, is I'm going to actually directly use the file path in a function to import this data. I'm not going to switch the working directory yet. I'm going to do that in a second. Okay, so let's look at how we're going to load this data. So we're going to, first of all, notice on the left, always the data object we're going to store it in. We're going to store it with the assignment operator, the result of this expression on the right. So read.csv is a very useful function. So note that when you start typing in functions, you kind of get this list and you can kind of arrow over and you can hit, I think, tab or enter. I usually hit tab, and then it will kind of fill out the rest of the command that you want for that function. And notice it even put parentheses for me. So now it's expecting that I put whatever I need to on the inside of that function. So I'm going to open up quotes because you need to input it as a string command. And I just pasted it. And what I'm also going to do, I need to get the name of this file. Let's see. Rename. Okay. So I'm sorry, I'm just making sure it's still recording because I accidentally flipped on airplane mode. I think we're good. Okay. So I got the name of the file right there. And I'll note this, I don't know how it is on an Apple, but this really annoys me. The Windows by default has the backslash. R only accepts forward slashes. So what we need to do is we need to switch each of these. And if you hit Control F, you can go ahead and use this find and replace like that. So anytime I copy in a file path, I usually have to do that. And so, there I just put the full file path. And at the end, I put the data set with its file extension .csv. Notice I'm using the read.csv function. So, if this was like a .sav, which I think is SPSS, it wouldn't work. You need to use a different function like, read.spss. I made that up. I'll show you guys how to install or import data with SPSS files next week. I actually don't know at the moment. I've never tried that, but it won't be too hard to figure out. But I got to find the right function and then, have the right file extension, and then you're good to go. So here we're going to be doing CSV. So I execute that line of command. Notice it doesn't print anything, but up here, I now have, you can see my environment. I have a new object. It's called DAT. I named it DAT, and it's got 170 rows of data, and it's got 18 variables. You can hit this little down arrow, and it's very useful. Let's go ahead and just actually look at. So, you can look at your data in Excel. I think a lot of people probably prefer that. Excel is just like a wonderful program for data organization, moving around. So, you can see we've got different variable names. This data set's got each observation is a country, And then it's different things about their diets. So has a few country level variables in the columns, right? So you can look at your data there. R also has, if you click, you see how my mouse is doing that little clicking motion there. If you click there, R also has this, and you can look at the data there. So that's also useful. I will say though, Excel is a little bit better. It's just, this can be kind of slow and laggy sometimes. So I usually will prefer to look at my data in Excel. Now you'll also see that so let's get to this DAT. Let's just do this real quick. Let's say class, and I call class on DAT. DAT is a data object called a data frame. And so what a data frame is, it's basically your traditional database, right? Each row is an observation, and each column is a variable. And so, we have 170 countries in this data set, and we have 18 pieces of information about each country. And then, how you can think of a data frame. So look at country. This is a character vector. And specifically, you can see the first few arguments. You go to animal fats, that's a numeric vector. So remember, a vector is basically storing some values. Now, you can't mix character and numerical vectors, so it has to be one or the other. There is, R is a very advanced programming language. You can mix them in something called a list vector. But generally, you're going to have like one type. So a character vector, integer vector. Well, actually, these are numeric vectors. So really similar to an integer vector, except you can have decimals here. So those are a little bit more flexible than your integer vectors, the numeric vectors. And you can see real quickly, you have mostly numeric data, and you have really the country is not really a variable. It's really kind of like, who are you analyzing in that row data? And so at this point, I want to circle back now and show you a very useful thing before we go on to analyze this data. So I was getting earlier at the working directory. So I can't, if I were to try to load this data set, I'm going to get an error. And it says there's no file that exists. And that's because where R is looking is in the working directory. So if I went and dropped this file in this folder and then re-executed this command, it would actually work. But we actually have to change the working directory if we want to. You could use this command if you had the working directory into like the right folder. So for us, that would be the data folder. But there's a useful thing called R projects. Now, I suggest that every time you work in R, you work in a project. So if you come up here, you'll see it says there's no project loaded. And these little blue cubes, that is the symbol for a project. So now I click, I'm going to create a new project. Oh, do I want to save these changes? I think I do. I'm going to save these changes. Now I'm going to do a new project. It's going to take a second to pop up. And what I suggest you do is you come here to existing directory. And then you want to browse to the right spot on your computer. So I'm going to come to the R labs. And I want my project to be there. So now I'm going to create it in there. And you don't want to put it in the data, don't put it in the output, put it just in the general R folder. And now I've created my first project. And you'll see it just took the name of whatever the folder you titled. So mine was called R Labs. And look, the files, it's now loaded and it's showing us everything that's in this project. So you can click into code and all that. You can go into data. And what we're going to do is we're going to open the code file from the files pane. We're going to go back down to where we were. And now we're going to run the git working directory. And you're going to see it has just updated where R is looking for files. There is a command called set working directory. I think it's set WD. and I didn't put anything in there, so it gave me an error message. So that's one way to do it. You could literally manually do that, but I think when you create the project, it's much more useful. And you'll see once you get used to these projects, you never can work another way. So I definitely suggest always saving and starting your work in R project, because what happens is when I close my project, R will open up to the same exact spot I was with all my data sets, all my analysis, the plots are open, everything, which is a really, really nice feature. Now, I could, read the data this way, the long way, but I have a project. So I'm going to execute this. It's going to be an error because, again, the project is looking in this folder. But really, relative to that folder, I need to go into the data folder / file name. And now R will be able to load my data. Okay, so now let's do some basic exploration. So data is an object. We're going to treat it as an input to functions. So we've got the dim function that stands for dimensions. So I got 170 rows and 18 columns. Rows are always come first. I can look at the class. It's a data frame. Names, this is very useful. I can look at the variable name. So there's 18 columns, right? So notice what this really is, names, this returns actually a vector. Like I could actually save it and store this in something called D. And then I could call D later. So the reason I bring that up is because you'll notice, look, it's kind of, when we were looking at vectors earlier, how it was kind of numbering them. Usually, because our commands are so short, you only saw the one. But when it goes on to the next line, R will tell you that seafood is number 6. So you can kind of count like fruit is number 7, recovered is number 16. So that's what the numbers there kind of are telling you. They're indexes. The structure function is really useful. It tells you what kind of variables do I have. So, you can get that at the down arrow up here as well. So either way, but you can see I have all numeric values for the most part, other than one character vector. And summary, look at this. Just like that, you can get the mean, the first quartile, median, mean of every single variable. So this is why, R is so powerful. How easy it is to get that kind of information. And think about it. If I had a new project, literally all I would have to change is the data read-in. And all of these commands would work just the same because I'm calling the object dat. So I usually stick with dat, and I will throughout this course. And it makes reusing code really nice. So you can kind of go there, do some exploratory analyses, and you can subset a data frame. Now, earlier we were doing subsetting of vectors. But this thing, it's not just one dimensional. A vector just has like, say 10 elements. But a data frame it has 2 dimensions. It has rows and columns. So when we subset, we need a comma. And the first argument or the first position is the columns. So if I do this, it's going to tell me, it's going to give me the first row of data only. Row of data. So for Afghanistan, I can see their animal fats, their animal products, yada, yada, yada. So that's the first row of data. If I want to see the first 2 rows of data, just like before, I can create like a little vector. And now I'm getting the information for Afghanistan and Albania. Maybe I want the first column of data, which is going to be the country names. Maybe I want the first 3 columns of data. So it's going to be 3 variables, right? And we know the first is country, animal fats, and animal products. Maybe I want everything except the country name. And look, so this is not really made to view big data sets. So you can see it runs out of room, so it starts printing down there. So again, I definitely think Excel or just go into that view option where you click over here is a good way to look at your data. Now you can also call commands for certain columns. So, C again is a vector. I create a vector here. So if I actually run this, you'll see the output is 2 string variables. And these string values, they happen to be the same as our variable names. So I do that, and I can actually get out those exact variable. And now I have like a new smaller data set. I could even store this in DAT1 if I just wanted like a smaller data set to work with. And now you can see 170 rows, but only 2 variables. Okay. Another useful way to look at variables is this $sign operator. So if you start typing like dat $, you're going to notice that you get all the variable names pop up, and you can call your variables in that manner. And so you see here, you know, you got a couple NAs. Those are R's missing values. So if I were to call the mean on this, well, we'll do this in a second. Talk about NAs, but that's how you identify them in your data sets. Okay. So at the very beginning, I was talking about Boolean expressions and how useful they can be. So let's look at some examples of use of Boolean statements. So first of all, let's just look at one column of data. Okay, it's all numeric, no missing values, all decimals. Great. So what we're going to do is we're going to call the median. So the median is a function. You got a mean function, all the main descriptive statistics, they have functions. Some of them, the names are not obvious, but most of them are pretty obvious. It's like, you know, min and max will give you what you expect. The median will give you what you expect. So inside the median function, I'm going to look for the animal fats column. I want the median of the animal fats column. And so right now, all I've done, I just executed this right part. I haven't looked at anything to the left of that. And so that's the median, 0.11685. But what I can do is I can combine these into more complex statements. So what I can do, if I execute this on the left side, it's a vector of 100 and something values, right? So what it's going to do is it's going to take every single value and it's going to compare it and say which are bigger than the median. And the median is just one number on the right. And when you do that, you see you get a vector of trues and falses. And so half should be true, half should be false, right? Because the median splits the data into, you know, 50% below, 50% above. And okay, what are we doing here? So now what we're doing here is we're basically taking this command and we're going to notice this right here is that entire line above. So what we're going to do is we're going to take the dat object, which again is our data frame of all the data, and we're going to subset it. You know, you see the square brackets, that's what that means. And we're going to subset it with a series of trues and falses. And so every time it's true, we're going to keep that data point. So I'm going to execute this and I'm going to save it in DAT1. And so you can already tell, look, DAT1 has half the observations as it should. I can call the dim to confirm that. Now I've only got 85 rows, still 18 columns, because I didn't subset over here in the columns, which would be after the comma, right? Okay, now let's look at some descriptive statistics. So I'm going to throw a research question at you really quickly. What are the biggest predictors of obesity in a country? And so, you know, if that's the DV is obesity, you usually want to start probing your data with the DV, right? So there's a mean function. Now I can call the mean on obesity, but look what happens. It returns NA, missing. Why is it returning that? So, you know, anytime you're not sure what's happening with the function, again, you can do the help menu with a little question mark, and you can read over here, you know, what's going on. And so, you know, if you read this a little bit, you'll be able to see that there's this extra argument we can give to the mean function, na.rm. And what this is it tells us whether NA values should be stripped before computation. If we don't remove the NA values, well, then it's going to be an error because you can't, like, it's a missing observation. You can't like add it or, you know, so again, I'm going to just highlight and run that one on the inside there. And you can see, look, there are NAs. So I need to tell R to ignore the NAs, to remove them. And I do that by adding a second command, and out comes the mean, 18.7 for us. But what if we don't want to use so many decimals? Well, options, digits will allow you to control that. And we can call for the standard deviation. Notice you're giving it the same NA to RM. You can call for the variance, which of course is going to be like 89 or 92, a little bit bigger than 9 squared. Sorry, it would be 81. But because it's close to 10, it's almost 100, right? So remember, just the variance is just the squared standard deviation. You can even come here. Oh, look, it's the next line. So you can see it right there. We square the standard deviation, we get the variance. We square root the variance to get the SD. And we have the max, we have the min. We can run summary on this one variable. Okay, so obesity is our DV. Let's go ahead and visualize it. So we have a histogram function. You just literally do the word hist and put in dat obesity. See how easy R is once you get going a little bit. I will say it takes some time in the beginning, but you hit this part where R just becomes so enjoyable to use because it is, it never changes, it never updates, and it's just very concise. I mean, that is much quicker than SPSS, right? We can also call a box plot. And so, notice there's not two variables here, just one variable. So, it's the traditional box plot. We call it the 5-number summary. 5-number summary because you have the Q1, Q3, the median, which is Q2. And then these are, depending on the settings, these are either the max and the min on the bottom, or sometimes if there's outliers, they kind of cut them off at 1.5 times the IQR, interquartile range. So again, I'm not going to go into that too much, but the interquartile range is the width here, the thickness of the box, a measure for spread or dispersion. So I would say there's a little bit of spread there, decent amount. Okay, so now what about our IVs? Well, let's say we think we've got a few important ones here. Vegetable, like obviously if you eat more vegetables, I'm going to hypothesize that you're going to have less obesity issues. So no missing data there, so I don't need the NA.RM. I can do histograms. I got good variance in that variable. And now we can even ask for descriptive information of all of our variables at once. So here, I've picked out these few variables to predict obesity, to look at that research question: vegetable products, sugar, milk, seafood, animal products. So what I'm doing is I have the DAT object, I'm subsetting it. I'm only selecting a few columns here. I'm going to store that in DAT1. So you'll see I got 5 variables in there. This is a pretty useful function. The head function, I use it a lot, actually. It just shows the first 6 rows of data, so you can kind of visualize and kind of look at what you're working with. And now let's say I want to calculate the mean for all of those IVs. Well, there's actually a call means function. So notice the M is capitalized. You've got to capitalize it. It is case sensitive R. And I stored call means in an object called means. So in my environment, you'll see it right there. And I can execute it. And you've got the mean of each column that way. Okay, so we can also get the standard deviation of each column. Now that's a little bit more advanced. I wish there was a call SD function, but there's not. Look, the apply function, I would consider this an intermediate to advanced technique, the apply functions. There will be a day where you want to come back and learn them. As you start learning R, I wouldn't worry about it too much. I'll give you some code that has an apply function in it, and you can kind of just use that. But to briefly describe what apply is, remember, you can always do ! apply, and you can read about it over there. And often though, like I find reading about this stuff online is just a little more helpful. If I'm really trying to learn something, because this stuff is a little, I don't know, written for computer scientists or something. Not as easy to follow as a walkthrough online. So what does the apply function do? It takes as its input a data set. We're telling it use that one. What the apply function does is it applies some function across all the rows or all the columns in a data set. So margin equals 2 indicates columns, 2 indicates columns, 1 indicates rows. So what I'm telling it, I want you to take the DAT1 data set. I want you to take every column by itself. I want you to use the standard deviation function, and I want you to throw out missing values. And so when I do that, it's going to give me the standard deviation of all of those variables. You can go ahead and do the same for the max, the min, etc. Now, this is where R gets really powerful. When you can start combining these steps into, you can create entire descriptive statistics tables pretty quickly. So here's what we're going to do. I'm going to create a data object. I'm going to call it descriptive.data. The C bind, that stands for column bind. So it's going to take a column of data and it's going to combine them. And so like, the means, it's a vector of 5 values. SD is a vector of 5 values. If I run the cbind argument function and put those guys in there, it creates me a little descriptive statistics table. I've got the means, the SDs, the max, and the min. And I can store that in a data object right here. So it's calling it like a, it's funny. It's kind of like a data frame. I probably would usually wrap this in a data frame. So notice it's really awesome when it's a data frame because you get the observations and variables. You can down arrow it and all that. This is just actually, it's storing as a matrix. Like if I were to run class and then put descriptive data, it's a matrix. And that just has to have all numeric values. But I typically prefer to work with data frames. And so, you can see it pop over here. It changed when I put the data frame argument around it. Okay, I'm going to delete that out. Just leave it as a matrix for now. And I can also do handy things like I can round. So round has 2 arguments, the things that you want to round, and then how many digits. That stands for decimals. So I rounded it to 2 decimals, and now it's a little bit more clear to look at the data, right? You can put 1 there, you can even put a 0. But note, I haven't actually saved or updated the descriptive.data data frame. So you would have to assign this to descriptive.data if you wanted to save it. And then, we can look at the dimensions, of course, and all that. Now, let's say you want to export the data. So what I'm going to do, I'm going to export it to the folder we have called output. And again, if you don't have an R project, this gets like really annoying because you always have to figure out like how to set the working directory, and you have to constantly be worrying about it. If you have an R project, the working directory is just the home folder here. And in that home folder, there's a folder called output. So I can just go ahead and add output /, and I'm going to call the file descriptive statistics.csv. So that's what I want to call the file. It's where the file is and output, and what I want to call it at the end. With the file extension, you need that. And then it's going to be the descriptive.data object. And the function we use is write.csv. So look, I'm going to go into my output folder, see it's empty. I hit this, and there it is. Just like that, it created it. I'm going to go over to my project. I'm going to open it up. And you see you can create pretty quickly descriptive statistics tables like this. And because R is a programming language, you could change the output and formatting to be whatever you want it in R. So very useful. Okay, so far we've only had numeric data. So let's say we want to use a categorical data. Well, we have no categorical variables. The first really is an identifier. It's really not a variable. It's 170 unique values. You really can't use that, right? So that wouldn't qualify here. But what we can do is we can create our own categorical variable. When you have numeric data, you know, remember I was saying you can move down the levels of measurement. So if you have quantitative data, it's very easy to turn it into qualitative data. We'll be doing more of that this semester. So let's create a categorical variable. So what we're going to do is we're going to create a binary variable that is 1 if a country is in the top half of meat consumption. So we're going to store it in a new variable called, so this is how you create new variables, by the way. I have the original data set object, and then I put $, and I just put a new variable name, meat.binary. You look over here, you won't see it in the data set. So I'm just telling R, I want to create a new variable. And what do I want to store in that new variable? If else, a very useful function. The first part of if else, it needs to evaluate to trues and falses. And so what I'm saying here, if the value inside the meat column, if that particular value is bigger than the median, well, that's going to be a true. Otherwise, it's going to be a false. The first thing that comes is what do we say when it's true? So if it's bigger than the median, I want a high meat consumption variable. If it's less than the median, I want a low meat consumption variable. So now I've got 19 variables, and it's going to throw it on the end here. And notice it's a character vector. There's only going to be 2 values in it, low or high meat consumption. And now I can use a table function. You can use that on numeric data too, but it's not very useful to look at a table of numeric values. But here you can see, okay, it's split it at the median, so I've got an even 50-50 split. I can also, if I take the table function, by the way, you can actually store this in an object called X, which I find pretty cool. And then, you know, in the next, if I take that object X, which is this entire table, like X is the entire table. If I execute X, the entire table comes out. If I put X into the prop.table, that stands for proportion, will give me a percentage. And so, you know, you can also just directly input the table function inside the prop.table function, you'll get the same result. Okay, so far we've been looking at univariate descriptive statistics. Remember, univariate, uni means one, variate, variable. So a univariate distribution or descriptive statistic focuses on one variable in isolation. So, you know, a bivariate, of course, will focus on how 2 things are associated or how they move together. So we can look at a correlation matrix. So we're going to call this, I think it's going to give an error message. Yes, because it says X must be numeric. So X is just kind of its generic, like whatever your input is, here it's the dat object, they must be numeric. We got an issue here because we have a character vector. You can't look at the correlation of a string with a bunch of numbers. So I'm going to tell it to do everything except for the first column. And furthermore, use equals complete dot observations. I can't remember what that is, but you know, you can always question mark core. And let's see, complete dot observations. So use, it looks like you can do everything. So if there's missing values in there, you're going to get an error. So I think this has something to do, all observations. So what complete observation is, let's see, I think, oh, it tells you right here. Complete if uses, then missing values are handled by case-wise deletion. So like, let's say that you have a missing value in the meat variable, and when you look at vegetables, you're just gonna have to drop that entire, like, even if you have the vegetable value, you can't do a correlation with the missing value. So you would just drop that observation. So that's what it means. If you're missing a data, just throw it away. Without that, you'll get an error because it won't know what to do. Looks like I'm still getting an error. Why am I getting an error? Really? Okay. That's because I created a character vector. Okay, so what I need to do then, I need to get rid of the first and last column. So I'm going to go ahead and say everything except the first and 19th. And you get out this matrix. Now, it's a lot of information. So the correlation matrix, 18 variables, 17, whatever it is, it's just too much going on. And you can see the display of it is kind of not even easy to look at. So what I'm going to do first, get rid of some of these decimal points. And secondly, so the round function, right? I just put this entire statement, I just put inside the round function and ask for 2 digits. Secondly, I just asked for the second, third, fourth, and fifth columns. So now, like annual products and annual fats, highly correlated. Cereals have a negative correlation with annual fats, etc. And I guess this is another way to do it. So you can also ask for this set of specific variables and, make a correlation matrix like that. And then, okay, and then we can also do some t-tests of association. So a correlation, it takes 2 numeric variables. A t-test and a correlation, it does tell you there is a p-value there. You can actually say whether they're significantly related or not, but there's also the effect size, just this magnitude of the effect. The t-test, it's for a different case. When you have one continuous normally distributed variable and a binary categorical variable. So the correlation, 2 numerics, the t-test is a statistical test that will tell you whether a continuous normally distributed variable and a binary, it has to be binary categorical, are significantly related. So, it is bivariate, right? Because it's just 2 variables, ignores everything else. So there's this function called bi, and it's pretty useful. So I'll first execute it. It gave me the mean of the obesity variable according to whether they eat meat. So if you're in the high consumption meat category, this is your obesity score. If you're in the low, that's your obesity score. It broke down the mean. I can also do the same command, but for the SD, the standard deviation. And finally, I can run a t-test. So here in the X, I'm basically, there's actually an easier way to do this. Hold on, let me delete this. Easier way to do that with code. We can write that obesity, and then I can write squiggly thing, a little tilde, and then I can write that meat binary. And so now what I'm saying, I'm kind of like treating obesity as the DV here, and this is the IV. So in R, the squiggly thing, we'll see this in regression. You'll get pretty comfortable with that in the next few weeks if you're continuing to keep up with these videos. This is saying obesity is kind of like the continuous variable. That on the right, meat binary is going to be the categorical variable. And there you go. That's how you do a t-test. So, the p-value less than 0.05. So they are significantly related. And you can just tell in the numbers, yeah, there's a pretty big impact based on meat consumption. And you can read question mark t-test. T-test is a function. So, you can have all the help menu over here. Now for data visualization. So I showed base plot earlier in base R. We're going to look at ggplot, which we installed earlier. It makes pretty nice and customizable plots. So that's a histogram. You can see there's kind of this bimodal thing. I wonder if that bimodal is due to meat binary. Actually, watch this. So we can actually, we're going to actually explore that because we just saw those patterns. Histogram of DV split by meat consumption. It would be cool if it actually worked, like I'm hoping. Oh, you know what? Actually, sorry, I have it down there. Sorry, I used this code a while ago. I forgot. I've got it down there. Okay, cool. So I'll jump back to the idea in a second. So you got a histogram there. And you can also do a density plot. It's kind of like a smoothed histogram. So you probably, for this case, prefer the histogram. Now, what I'm doing here is let's split the DV histogram by meet binary, which seemed to have a big effect. In fact, it was statistically significant effect in predicting obesity, right? So I'm adding color, I'm mapping color to this categorical variable meet binary. I'm also going to map fill to meet binary. And let me do that. And look what happens. You can see the low meat consumption is accounting for the bimodal distribution. But the high meat consumption is on the right. So you can see how they're kind of splitting. That's why there's two peaks here. Now the genome density, that basically is what a density plot is. But the alpha 0.3, that makes the alpha makes it transparent. So look, I can't give you a full education on ggplot at this point, but there is a tremendous amount of resources online for learning and using ggplots. And so, okay, we can also do a box plot where we look at the difference, and there you can see it just jumps out at you. Obesity is just higher for the high meat consumption, a lot lower for the low meat consumption categories. You can, do sideways, all kinds of things. We can do scatter plots. So we've been using a categorical variable. So what I'm trying to show here is you can store a ggplot in an object, just like you did everything else. And then you can call scatter, and there you got a scatter plot. So you can see a positive trend in the data, right? As you consume more meat, there tends to be an increase in obesity. And the cool thing about when you store it is now I can add, I can impose a linear regression line right on top of it. And look how easy that is. There you go. You've just plotted your linear regression line, and we can, this is called a lowest curve. You have to look at the default settings. It's basically a smoothed regression line. You can see it kind of bending with the data. So it looks like obesity has a positive correlation with meat up to a point. And then once your meat is kind of in this 4 to 8 range, it kind of levels off. And you'll notice the error around the lines. Notice when there's few data points, we're not too confident that our line should be at that prediction, right? So there's wider, but when there's a lot of data points, the error bars around the regression line get a lot smaller. We'll be talking a lot about that this semester. Okay, so, we can put a lot of different commands together, and, you can get something that can go in a journal. Look how little code that was. So I'm going to leave it to you to come and figure it all, figure out what all this means. I think most of it's pretty straightforward. Definitely happy to take questions as you have them. The last visualization thing I want to show you is this thing called a scatter matrix. It's pretty cool. You create a scatter plot with, you have to have all numeric variables, and you create here, it's like what, a 5 by 5 scatter plot. So for obesity and animal fats, I can look at the scatter plot there. Kind of a strange relationship, huh? Because there's definitely a clustering down here. So you can see a positive small relationship maybe there, but it's kind of funny, these points pan up there. Here you've got a strong negative correlation, right? You can see linear impacts here between obesity and, in this case, sugar. As sugar consumption goes up, seems like a pretty decent slope there. So that's a pretty useful tool, this scatter matrix. And we'll conclude by fitting a linear regression model, and R, it couldn't be easier. You just do ln for linear model. Notice when we were adding the linear regression lines, it was LM up there as well, linear model. DV on the left, squiggly in the middle, IV on the right. Obesity being predicted by meat. And then you have to tell it what data set. And look, you can run just LM. You're going to get the intercept and slope. Intercept and slope. The two things you have in any linear function. Now I can store it in mod. You store it in mod, it calls this, it's a data object called a list. And what that means, it has all different kinds of things in it, all different kinds of output. List objects are kind of complicated, and that's kind of like an advanced programming thing. So don't worry about list objects and learning about them. I would focus on vectors and data frames. Those are really what you want to learn. Now I can call the summary function on the mod object, and look, it's going to print out, I've got my intercept estimate, my slope estimate, I've got the errors, and we're going to be talking a lot about that this semester. Just wanted to show you how easy it is here. And then you can add many variables and like that. So this is kind of like a tour where we're going to go in the next few weeks. So next week, we'll start with simple linear regression. We're going to learn how to interpret all this. And the following week, we fit a multiple regression model, which is the same thing. It just has multiple IVs now. So we have several IVs, whereas in the simple linear regression, we only had mean. All right, well, that's all for today. Definitely don't hesitate if you have any questions about R to reach out to me or your CA or TA.